parts. The first part's going to be 3 talks from 3 Xarray core maintainers about cool new features that they've either implemented or in the process of implementing. These features are aimed at making Xarray more flexible. And a lot of this work has been funded by the Chan Zuckerberg Initiative's essential open science software. First, we will start off with Aureliana Barghini, who's a scientific software programmer at Be Open. She's contributed to Xarray, and I think other big contribution is to CFGRIB and many other packages in the remote sensing space. And she's going to tell us about a new backend plugin infrastructure for Xarray. Aureliana.
Hi to everybody.
Oh, just one last thing I forgot to mention. We'll have a roughly 50-minute talk followed by 5 minutes of questions. Feel free to ask technical questions. We're also interested in hearing how these new features help you really extend your science and workflows. Thanks, Aureliana.
Thank you very much. Hi, I'm going to present the new Xarray backend API. And that is really useful to add new backends for reading new data type, new format file. Yeah. You can find this notebook here. And if you want some more detail, you can see the backend documentation of Xarray here. Now, as you know, Xarray can read different type of files, specifying the engine keyword inside the open dataset. And you can read the grib, netcdf, and ZAR. And for each available engine, there is an underlying backend that reads data and packs them into a dataset. Currently, there are many internal backends developed, netcdf4, SciPy, ZAR, and some external backends that have been added after the release of Xarray 0.18 with the new API that allows to support to add backends without adding any code into Xarray. And for example, we have CFGRIB that previously was an internal backend, but now we are going to externalize it. TadDB, RioXarray, Xarray Sentinel. Now, why using the Xarray backend API? Well, first of all, because your user don't need to learn any new interface because they can use open dataset Xarray that is quite known. And then with a little bit of more effort, you can have lazy loading with Dask. And finally, it's easy to implement now because you don't need to integrate any code in Xarray. Now, I'd like to start with the backend without the lazy loading because it's the easiest one. And well, all you need to do is to implement an open dataset function that reads files and put it inside a dataset. Then this open dataset function must be put inside a container class, my backend that inherit from an Xarray backend, Xarray class, backend entry point, as you can see here. Okay, and let's see how we can use this this class. This class can be used in 2 ways. The first one is declaring the class as an external plugin in the setup.py. The second one is passing the class to the open dataset function using engine parameter. Clearly, I suggest to use the first one if you want to do something more structured inside the project. But the second one is really useful if you are doing tests or doing a tutorial like me now. So we are using this interface. Okay, let's start with an example. Okay, here I implement a backend for reading binary files, and we have got two sample files. The first one is in integer, the second one in float. Now, and this is my entry point. As you can see, it's really very short, the implementation. Here I use I use NumPy from file for reading it. I open the file, I put it inside a NumPy array, I define my variable, I define arbitrary coordinates since I don't have coordinates here, and I return a data set. Let's check if it works. Here I open. Okay, it's take a little bit, it works, but clearly it's a little bit memory demanding since we are reading all the file in memory, as you can see. If we want to read the, if you want to read the float file, then we can pass this key to open that array, and Xarray will pass it directly to the backend here. Yeah, I forgot to say that. Okay, the signature here of open dataset must be the file name, drop variables, that is mandatory, but now we are ignoring it. And this is a specific backend parameter that we can pass inside open data array, and it will be passed automatically to the backend. Okay, and it should work. I hope. Okay, just to be sure, let's try to use the selection with the coordinates. Okay, everything's fine. So I think that we can have a look to the lazy loading. Yeah. Let me restart the kernel. Okay. Well, if you want to make your backend effective with the big data set, you need to implement lazy loading. And for doing that, you basically need to implement a row indexing method for reading blocks from disk. And this is on you because you know how to do it. And it's the big part. Then we have to implement some glue code to make it work with Xarray. And that's glue code is put your row indexing method inside a backend array subclass, and replace inside your dataset the NumPy array that we were using before with your backend array class subclass. Okay, let's see an example. Okay, the binary of the binary backend array that is going to replace then the NumPy array. And the binary backend array must implement the row indexing method, a getItem method, that this is a wrap of the row indexing method with an Xarray helper function. And well, if you don't need to do something particular, you can also copy paste my example and it will work. So all the logic is inside the row indexing method. Then you need to have a shape attribute and the type attribute. Okay, and this is my implementation of the binary backend array. So here I take the input in it, the file name, the shape, and the lock. And this is the getItem that basically transform the Xarray indexing in something that my row indexing method can use. And this is the row indexing method. The input is a key. It must be taken input a key that is a tuple containing or an integer or slices. In my case, since I have only one-dimensional array, it will be a tuple with only one element. So I select the first element, and I implement both my logic for both slices and integers. So if here from file I need to compute offset and count. Then if the slice I just do this computing, and for integer this one Then with a lock, I read the part of the data that I need in a NumPy array, and I return this one. Okay, how is going to change my backend entry point? Well, backend entry point is not going to change too much. I just need to compute size and shape before, because I need it inside my binary backend. I instantiate my binary backend array. Then I have to wrap it here with a helper function of Xarray that manage lazy loading. I put in my variable and I return my data set. So that's all. Let me run this else, sorry. Okay. So we can test it. Okay. It seems it's working. Clearly, we haven't read in memory all the data because the memory occupation is very low. If I perform the min, we are using the chunks, so the occupation memory footprint is always slow. And let's check if the slicing works. Okay. And if I load into memory, clearly the memory footprint will be higher here. You can see it here. Okay, it takes a little bit to load it into memory. Okay. I think I've finished.
Great. Thank you, Aureliana. That was a very clear talk with very good examples. I think we should get these examples in the Xarray documentation or tutorial somehow. They're very clear. So now it's time for questions. Again, we invite both technical questions and also even just comments on how you might use this new backend feature. Please raise your hands or type it into the chat. While we wait for questions, I have one quick one for Aureliana. So you've demonstrated read support through open dataset. Are there any plans for write support, for example?
Can you repeat? Sorry.
You demonstrated read support through open dataset. Are there any plans, or is there a way to do write support?
Okay, for write support, we started working on write support. I think, well, it seemed to be a little bit shorter, the work on write support. And well, we don't have any defined plans about it. Also because the users of the write support are really limited. So I think we don't really need to have a sophisticated interface for that. But I think also this will need a little bit to be reviewed. Yeah.
Thank you.
No, sorry.
Okay, it doesn't look like there are any questions, so I think we'll just continue and then we'll maybe have an extra break at the end of the hour. Thank you, Aureliana, again. That was a really nice talk. Next up is Benoit Bowie. Benoit is a freelance programmer. He's been very involved with Xarray and surrounding ecosystem, especially Xarray SimLab. And most recently, Benoit has been working on extending Xarray support for indexes. And so this is going to be a very exciting new feature, and he's going to give us a work in progress talk, really. So Benoit, I'm going to share your screen.
Yeah, thanks, Deepak. Let me share this. All right, can you see it?
Looks great.
Good. Yeah, hi everyone. Yeah, so I'm going to talk a little bit about Xarray explicit and flexible indexes. So first of all, fresh reminder, I'm sure you already know about that. What is the Xarray data model? There is an example here below, an illustration of what is an Xarray data set. And here an example taken from the tutorial. So basically we have data cubes, multiple dimensions, and And then we have, for each of these dimensions, we can have coordinate labels. And let me just go through some of the features that I'm sure you also already know about, like label-based data selection. It's a nice feature in Xarray that allows you to extract some data from the data set using the actual coordinate labels and not the positional indexes, like selecting a given latitude and longitude value or time value. You can also select not the actual value, but some kind of fuzzy selection here with the method nearest. Another example here is two different data arrays that we can sum up to each other. And Xarray is smart enough to actually do the computation only for the overlapping part of the two arrays. So there is some kind of automatic alignment. So those are two examples. There are many more examples, like you might know group by, doing interpolation, resampling, differentiation, integration, and so on and so on. And all these operations in Xarray have in common that they all rely on panda index. So this is kind of implementation detail in Xarray. It's actually Xarray internals. You might be aware that Xarray relies on panda indexes, but actually for a Xarray user, she or he might not even notice that we're using Xarray indexes here. So far so good. It works well for many cases, but there are some cases where there's some limitations, and I'd like to go through some of them. First of all, for example, here, irregular data. So we have a bunch of points with X and Y coordinates. Well, that's not the ideal data set to use with Xarray, but we can use Xarray with this kind of data sets and leverage it, for example, to do some plotting, and we get the dimension labels here as an example. But for other operations, like you want to do selection using this, well, it doesn't work like it's not that straightforward, right? Because there is one limitation in Xarray. There can be only one index per dimension, and here we have two coordinates for the PTS dimension, so it doesn't work. What you can do, maybe it's there's a trick in Xarray that you can group the X and Y coordinates into a multi-index. Let's try. But then no, it doesn't work really well, because this kind of nearest neighbor selection is not supported by multi-index. So yeah, we're stuck here. There is another example here. Let's have a data set with large size dimension, like here X dimension with like hundreds of millions of data elements. And what's nice with Xarray is that it integrates well with Dask. So we could use Dask arrays with this. It fits very well. So in this case, it's okay. We can have a data variable sec with like lots of elements. But then what if we want to use this sec data variable as a coordinate and do some operations on it, like using the labels for selection and so on? We could do this like this, but then we end up with not Dask array anymore. It's a panda index. It's fully in memory, so you end up with a lot of data in memory. And there is some operations like this that might be not the most efficient one. So here just stopped the computation. And this is because, like, unlike a Dask data frame, there's no not yet an Xarray index partitioning, so it's not really efficient. There are some other more domain-specific cases, like dealing with geospatial data. Actually, coordinate labels with this kind of data relates to some coordinate reference system, but Panda Index doesn't have really features for supporting this kind of coordinate system. Also, some users use play with staggered grids, kind of different grids that relate to each other. it might be a bit tricky to use that with panda indexes. And yeah, maybe you have other cases. You're working in a domain where you have some issues with Xarray, like using panda index. So it'd be great to hear from you and have your feedback on this. Okay, so, well, there are some limitations, but it doesn't mean that we cannot use Xarray with these kind of data sets. We actually use it with some kind of workarounds. And most of the workarounds here is kind of hacking into Xarray. So what we use, we add extra coordinates or attributes, or we use data array accessors to store some more information objects. It kind of works, but it's not super ideal. Sometimes, you know, when you have an operation that takes one data set and produces another one, those kind of objects are not propagated very well from one data set to another. So there are some tricky issues with this. So maybe we can do better. And maybe one answer could be the bringing explicit and flexible indexes in Xarray. So this is something that is part of the Xarray roadmap for a while. It's now ongoing work, and also it's funded by first Xarray CZI grant. So what is it about? So there's two words here, explicit and flexible. Explicit means that we want to make indexes first-class citizens of the Xarray data model. So taking back the example here, the example data set, we could add an index section here along with the dimension, coordinates, and data variables. So that here it's really explicit that each coordinate may have a particular index. And secondly, so flexible indexes, it means that we want to provide Xarray index base class with some kind of API that we can use for different operations like data selection, alignment, and so on. And we can subclass this index. And we want also to provide some extension mechanism like the reading file backend, right? So taking back this irregular data set, data array example, you can see here in the index section, this KD3 index, it's not actually a panda index, it's a custom index that may live outside of the Xarray code base. And it's very efficient for this kind of data, for indexing this kind of data. And you notice here that an index may be built from several coordinates, not anymore for one single coordinate, and also possibly for multi-dimension coordinates, or maybe coordinates with different dimensions, like for the example of staggered grid. Okay, so this is very work in progress. I'm not going to go much more into detail here, but if you want to have more information, there is in the Xarray repository on GitHub some kind of design notes. And there is also an active project if you want to track all the issues and pull requests on the topic. I just want to spend here a few more minutes talking about a specific use case. It's a point-wise selection of irregular data. And this is something we've been experimenting also in a GitHub repository. It's called Xoak. So briefly, how does it work? Let's start with an example here. It's a 2D regular mesh with some latitude and longitude coordinates. And we want to extract some points from it. Like we can have a query point data set like this one, trajectory data with a bunch of latitude and longitude coordinates along a given track, for example. And how can we use this to extract some points from the 2D mesh? With Xoak, it's pretty straightforward. So what we need first to do is to set a new index, providing the latitude and longitude coordinates. And here S2 points, it refers to a geographic index. And then once we have this, we can call the selection and then just passing the query point dataset coordinates. And what we obtain here is a dataset that is consistent with the query point dataset, is shown here on the right. The black line is the query dataset, and the red dots is the extracted point from the 2D mesh. So just to mention here, Xoc is a dataset accessor, and most likely with the Xarray flexible indexes, we won't need this anymore. So we'll use directly the set index and set from Xarray. I just want to show you how powerful the Xarray advanced indexing is. So here it's the same kind of thing, but with a 2D query point data set. Let's say, like shown here in the right, a bunch of points on the Earth surface, and how to extract some a point from the 2D mesh here. It's actually this exactly like for the 1D case, so taking the latitude and longitude coordinates. Okay, so Xoc has also some experimental Dask support. So I have to talk about this because we are at the Dask Summit. What it means is that you could use for extracting points and do nearest neighbor selection, you can use chunk point coordinates. And this for both the query points and also the index points. So briefly, how does it work? So there's two stages. A first map stage where for each block here, we're going to call the query method from the index. There's 3 different indexes here. And in blue, this is the results from the query. So this is the nearest neighbor for each block. And then the second stage is a reduce but brute force lookup. So we're going to apply this Dask array argmin on this dimension. And then the final result in red is the nearest neighbors that are selected for each point in the query point data set. So it's pretty straightforward approach. It's quite simple. It's maybe naive approach. It works well sometimes, but often it works well like this tasks stream. But often, yeah, it fails miserably. But it's not because Dask is not great. Actually, Dask has a great library, but it's rather maybe because my experience with Dask is a bit limited. But it's also a very challenging problem, I think. So, like most Dask operations, chunk size matters. So if you don't have the right chunk size, it can go wild. And in this specific problem, there might be a lot of Dask interworker communication. And especially index, we are dealing with indexes here, which are complex objects. So they often have dynamic data structures. It's not always fully exposed to Python. So it's sometimes hard to get an accurate memory footprint. I think it's an issue. Might be an issue with Dask, but so it might be hard to serialize. So, which means that if we want to move an index from one worker to another, it means that rebuilding the index, which is it's not ideal. So yeah, I guess that's it. Maybe I just want to end not on a pessimistic note here, just optimistic way. I think all these indexes are something very exciting, and I'm excited to see what is coming ahead. Yeah, that's it. Thanks.
Thanks, Benoit. That was a great talk. Again, feel free to ask questions, raise your hand, or even just speak up. We're particularly interested in hearing use cases that you might have for these features. We have a question in the chat for, actually, I'm not sure who this is for. This is from A. McNichol. Are chunking heuristics complicated enough to be use case specific, or is there some best practices that could be determined at the package or community level? I'm going to ask for a clarification. Are you thinking of chunked indexes, or are you thinking of chunking of Dask arrays in general?
Well, I'm interested in chunking of Dask arrays more generally, but in the specific context of indexes, it's an interesting question too, especially considering indices are how we view into the data and the powerful way to make selections. So both.
Yeah, so I think it's a good question, but there's no an easy answer on this. Yeah, I'm not aware of all the chunking heuristics, to be honest. So I might not be able to answer very accurately on this, but I think it's a very complicated problem, and it really depends on the task that you want to perform. In this case here, of like point-wise data selection with an index, it's a very specific thing, and maybe for some other operation like I don't know, group by. So Deepak has been presenting task group by thing, and it's a completely different algorithm. So maybe the chunks there, the way to chunk the data might be completely different. The optimized way to chunk the data may be completely different. So yeah, it's really problem specific, I think.
Next question is from David Hayes. Do you see indexes being used directly for resampling operations, or are resampling algorithms too complex to use indexes efficiently?
Yeah, that's a good question too, and to be honest, I'm not sure yet of all the use case, like so how would work resampling in different domains. So I'm not exactly sure to
David,
guess,
do you want to unmute
yes.
and maybe describe your use case? Sorry.
So during this conference, I've also been meeting with the PyTrill group. I'm one of the core developers there. We maintain the PyResample library. I am also the person who tried to create the GeoXarray library. And I've also replied to some issues on the XOak repository about this. The use case is geospatial resampling, where I have long-lat coordinates. Maybe the pixels are not uniformly spaced, maybe they are. And all of this indexer talk makes me really want to use them. But then when I think about actually implementing it, all of my algorithms are lower level than that, where they're doing the indexing their own way to be most efficient and to do things intelligently with Dask chunks. So I was just hoping somebody gave me a magic answer of, oh yeah, it would work exactly like this. And okay, I'll implement that. Thank you.
Yeah, maybe I think that would be a nice use case and a nice try. Once the flexible index is available in Xarray, why not trying to subclass the Xarray index and implement your own logic into it and see how it works. I think that would be I would be really interested to see how it goes once it's ready. And we probably need a few iterations and feedback from users who want to implement some custom indexes, and you might be one of them, I think.
Yeah, thank you. I agree.
Milind asks a question: does regridding using XESMF solve some of the irregular grid problems?
Yeah, I think I have not much used XESMF actually, but yeah, it's mainly about regridding. So I'm not sure if it really use indexes to like some data structures that then could be reused for easily selecting data, doing some alignment and so on. It creates, I think it creates some weights that can be just reused to interpolate between two different grids. So it's slightly different problem, I think. I'm not sure yet how this could be reused as some custom index in Xarray.
Yeah. Would invite Tom to unmute and just comment. I think it's an interesting comment. Tom Nicholas.
Hey, yeah. I just wanted to point out there's another use case which people might not really aware of, which is interesting, which is that there's currently a lot of work by mostly by Justice on getting unit-aware arrays to work in Xarray, so that basically the arrays know when you're making this error, like trying to add apples to oranges or whatever. And it would be super nice if coordinates could also know these things, so that your spatial coordinate knows whether it's in meters or centimeters or whatever. And in order for us to be able to do that, then this indexing refactor, it would allow that basically, because then you could replace a standard pandas indexer with some kind of unit-aware indexer. I just think that's a cool use case that should be mentioned.
Yeah, that's a very good point. Thanks for raising this. Yeah, data selection with like using coordinate with some units, and then you provide indexers that maybe have other units, and then unit conversion is done on the fly. While selecting data is something that would be great. Yeah, definitely.
David asked another question. Do indexes get lost when operations are performed on the Xarray object, like adders do sometimes?
So by indexers, I think, David, that you mean index is what we call indexes in Xarray. Indexers is more the labels that we provide to do the actual selection. But regarding indexes, then they may be lost or maybe not. Like pandas indexes may be itself indexed. So you could reuse the same index. So in the result array, this will be just the same panda index object that has been indexed. But for other indexes, like a tree-based index, like KD tree or something, that it's less straightforward. So I think from one operation to another, you will have to rebuild the index.
And perhaps the last question for this segment, question from Gerardo. Does the new index implementation affect how Xarray structures are translated into pandas data frames? Or does it purely affect how we select data in Xarray?
So for the first question, I think it shouldn't. So it shouldn't bring any breaking change or affect any behavior like that. And Xarray already is plays well with panda indexes, so it should still be the case after the refactoring. So I don't think so. And for the second question, yeah, it may affect how we select the data. It's actually extending the Xarray capabilities, but not changing the actual capabilities.
Thanks. I'm going to invite Andrew Thomas to unmute and comment on his use case for sparse indexing. It seems like an interesting discussion.
There's nothing explicit that I can elaborate on, but I've been paying careful attention to the developments related to that nested wrapping of coordinates and indices, and sparse arrays have been mentioned as part of that stack. There are potential use cases in radio astronomy, which is my field, that would make sparse indexing, especially on multidimensional data, valuable. But at this point, it doesn't seem clear to me where that fits into the Xarray ecosystem, especially considering some of the data formats we have are not regular. So that adds back into the initial discussion. So just throwing it out there to be part of the conversation.
Thanks.
All right, if there are no further comments on that, I think we can move to our next speaker, who's Justus Magen. Justus is a Xarray co-maintainer, and he has also worked a lot on Pint and a Xarray extension called Pint Xarray. And today he's going to tell us about work on sticking ducks in Xarray objects and why you might want to do that.
Okay. So yeah, I'll give a brief overview of what we're doing with the Xarray integration into Xarray, which includes the Pint and sparse we were talking about before. And I first go into detail of what we mean by duck arrays, and also what we mean by that in the case for Xarray. And then we'll look at the current status of integration into Xarray. And finally, some additional support functionality. So first of all, what are Duck arrays? First, the term Duck array refers to the term duck typing, which is used to describe that instead of checking types, we're checking interfaces. And typically we use either just try to access the attribute, and if fallback if it raises an attribute error, or we use the hasAttr or getAttr functions. There's also the case where we could use abstract-based classes or mixins. Just something to be aware of. So with that, Duck arrays are arrays that implement the NumPy interface. This allows us to have these arrays behave like NumPy arrays, but do something differently under the hood. They don't have to be ND array subclasses because we're using the interface, but ND array subclasses can be Duck arrays. And also because we're the interface we are talking about is pretty restricted. Duck arrays don't have to implement the whole NumPy API, which has some implications we'll see later. Also, this is not the same as array-like, which is just anything with which NumPy.array accepts, which can be either scalars or lists or something like that. So Duck array requires a few things: the endim shape and dtype properties, which are used to get some idea of what the Duck array looks like. And then some protocols. First of all, the array protocol, which is used to convert to NumPy. We use that, for example, with the $values property on variables and data array object. Also, I think immediately before plotting. And then we have the array ufunc and array function protocols, which are used to dispatch NumPy API functions. Such that, for example, a ufunc like the sign can be called on a Duck array and it returns a Duck array. Also, there's others like full-like or where or something, which allow us to return that Duck array. In the future, there could these two protocols could coexist or even replace array ufunc and array function, which is the array module protocol, or the newish array namespace. Yeah. Here's some examples for Duck arrays. There's of course the pint, which is physical units and an array with physical units, and sparse, which provide like dense representation of sparse arrays, but also QPy, which is instead of running on the CPU, we can use that to run on a GPU. And Dask is also a Duck array, but Dask is Dask support for Xarray precedes the addition of array function. So Dask uses a separate code path than the others. So with that, let's look at the status of the integration. First of all, to really know about this, we need tests, and Xarray has test suites for both pint and sparse. But because I mostly worked with pint, I'll use that as an example. So that test suite tells us that most work methods keep the Duck array as a Duck array without converting to a NumPy array, but there are a few exceptions. We heard about this in the previous talk, but DAC arrays will be converted to ND array when we create the indexes. So these functions don't allow us to have these and use the selection. This does not mean that non-dimension coordinates and which don't have an associated index and the data are converted. That just works fine. There's also a few functions and methods which rely on external libraries. Like for interpolation, we sometimes use SciPy, and that doesn't allow dispatching through array function. That might change with the array module, array namespace, but that's not quite there yet. And finally, we have a few functions in NumPy which are not covered by array function, which is mostly NumPy.vectorize, and we use that internally when interpolating missing values, or if you enable the vectorize option in apply_ufunc. Before NumPy 1.20, we also had troubles with the rolling functionality in Xarray, but since then the sliding window view function was added, and that allows dispatching. Just that Xarray has to implement that. So as I said before, any Xarray can or does not have to implement the whole NumPy API. So they tend to behave somewhat differently. For example, sparse does not implement the cumulative sum and product, and I think Dask has trouble with multi-axis median something. So not everything works the same, which is why we can use the pint test as an indicator, but doesn't generalize to other DAC arrays. So yeah, the support status for arbitrary DAC arrays are unclear. And that leads us to the DAC array testing framework, which is a work in progress right now, but I think could help us answer that question. So that module is heavily inspired by the pandas extension array test suite. And we use this to group Xarray's API into several parts and provide base classes for these, such that DAC array can, or DAC array library rather, can use or decide which parts of the API it wants to support. Also, this also can be done by a DAC array integration library. We use hypotheses, a library which allows us to define certain strategies, such that we can vary the parameters to the function we're testing, and that will then use that strategy to find a combination of parameters which cause your function to fail. And because it's pretty generalized, we can use this to check any DAC array or even nested DAC arrays. Like there's the possibility to have a CuPy array inside the Dask array, or even something that is nested deeper, like pint array, wrapping a Dask array, wrapping a sparse array. And this, again, the support status for any of these is unclear because we don't test that yet. Okay, and finally, there's some issue with the inline representation of DAC arrays. On its own, DAC array or the wrapper of a Dask array should contain the shape, dtype, and other specific metadata. But because the Xarray wrapper already contains the dims, dtype, and dtype information, that would be duplicated, which would waste valuable horizontal space. So here, each of these are inline representations. And as you can see, we have a special custom wrapper for Dask and also sparse and NumPy. And you can see, for example, for sparse, it has a shape and dtype information, but also the number of non-zero values and the fail value. And the custom wrapper will remove the shape and dtype information. Same for Dask. There's a name, shape, dtype, chunk size, and chunk type. And we remove that to only contain chunk size and chunk type. There's this here, which is different. It doesn't say chunk type. And that's because I think it was added before the chunk type was, or something like that. I'm not sure. We could fix that, but it would probably be better to use something else, which is the wrapper inline hook, which can be defined on the Dask array, and it receives the maximum width it is allowed to take, and allows us then to customize that for Pint, which is not included, and we'd rather not include that much other arrays. This is the inline representation, which is pretty much useless. There's a few values, but the most important one, which is the unit information, is removed because it's too long. So instead, we can define the wrapper inline and get a nice representation. This doesn't work with nested wrappers yet, nested Dask arrays yet, because we don't delegate to the wrapped Dask array yet. And with that, I'd like to wrap up and take some questions.
Great, thanks, Justus. That was pretty great and clearly highlights a lot of potential applications here with all these nested arrays. Do people have questions or comments? I wanted to say that the idea of using something like hypothesis, which kind of tries to explore the problem space, seems like a great way to test all these many combinations of arrays. It's kind of hard to ensure reliability in that case, I guess, when you have all these complicated combinations. Do you think that that kind of Dask array testing library would be kind of a useful library just for the ecosystem in general?
I'd say so, yes, because there are some tests, for example, for QPy in a separate repository, which does need special infrastructure, like it needs a GPU, and so we can't use it on the main repository. And also, yeah, it just tells us what parts of the API are supported.
I had a question. So related to all of these different types of Dask arrays, it seems like there's this question of how should these things be layered, sort of like, should I have my units around my Dask array, or my Dask array around my units and around my where does Xarray fit in, and what if those things live on GPUs? I'm curious if you have any thoughts about what the right way to sort of, I guess, make that easier, or how do we make that manageable?
So yeah, there's a few things to consider. For example, you can't use, you can't wrap, some DAC arrays don't support wrapping, like the QPy array, and I think sparse does not yet wrap that, allow that either. And then there's the thing where, for example, for Pint, in the specific case where we want to check the units, and the Pint array wraps the Dask array, then we can, for example, run the product function and get a result back. There's a chunk type mechanism which will run on an empty array, but for the product, where the shape of the array determines the unit, that is something which is difficult to do. For others, where, for example, the AstroPy units, you can't, because it's an ND array subclass, you can't have it wrap Dask. So there are some limitations to this, to the ordering, but mostly I think that's not clear. I think we need to have some sort of mechanism to decide which DAC array wraps which DAC array. Mostly because we have to, if you try to combine different, if you try to do something with two different DAC arrays, you have to decide which DAC array should take care of that that operation. Did that answer your question?
I guess, yeah. It seems like it's still a challenging thing to sort of figure out.
Yes, it is.
I have a question, if that's okay. I mean, sort of following up on that same line, and also thinking about something that Travis mentioned in his keynote. Is this, I think what I'm thinking back to is the characterization of the open source Xarray ecosystem as kind of foamy. I think that was the word that was used. So what I'm looking for is the place where someone can inject energy to make these decisions happen. Is it on PRs, or is it pinging you directly, or is it having an institution throw their weight behind it and put like resources on the problem? Or is there some type of, maybe the summit like this is the right place to have conversations about who should wrap who and get the package maintainers to agree where that's possible, and then identify cases where it isn't.
So I'm not sure where the best place would be. We have some discussion on the Xarray issue tracker, or even PRs on Xarray, but we also have some discussion in the Dask issue tracker. And I think we just have to find a place where we want to have that discussion, and where we want to figure this out.
Terrific. Thanks. Also, thanks for all the hard work you've been doing on NAP 18 and getting this to start working.
Thanks.
I mean, I'll just comment briefly on that. I think definitely it's a case where if there's somebody who has, like most things in open source, it's like if there's somebody who feels like they have like a really strong sort of need for the future and is sort of willing to sort of help get things organized. I think a lot of folks are sort of helpful to, or sort of willing to be engaged, but it does need somebody to sort of, the stuff does often need someone to sort of drive, someone to sort of drive it forward and sort of, write design documents, write code, schedule meetings, stuff like that.
So there's this data APIs effort, right, which I don't know much about. Is that kind of addressing this kind of question?
So I think that's something Stefan should answer, because I don't know too much about namespace.
I can comment briefly on this data APIs effort, which is sort of started by some folks from Quantsite. That was more around trying to find a way to say, like, like sort of like what should say like NumPy's, like what would like a minimal version say of NumPy's API look like if you sort of tried to unify NumPy and PyTorch and TensorFlow and Dask and everyone else, for example. They haven't really, the focus there has not been on handling this like layering issue, which I think is most relevant, I think, honestly, to like this community. It's not the people who write, I don't know, like say deep learning code, for example, they're mostly happy to just have a way to, they want to be able to switch between systems, but they don't need to layer them.
Okay, thanks. So at this point, we'll switch to the second half of our session, and I will hand it over to my co-host, Anderson, Banihirwe.
Thank you, Deepak. I'm assuming you can hear me, right?
Yep.
Okay, good. All right. So for the second part, we're going to switch gears and focus on user stories from non-geoscience domains. So Xarray is very famous in geosciences, and we thought that it would actually be interesting to have people from other domains come and share their stories and the challenges that they run into. So we have three speakers. So our first speaker is going to be Jack Leland, who's going to talk about Xarray in fusion energy research. Jack.
Cool. Thank you. Can you hear me all right?
Yes.
Cool. Let's get this going. Great. Lovely. So I'm Jack. I am a PhD student in the UK studying fusion energy at the Culham Centre for Fusion Energy, CCFE up here. I've just handed in, so I've got a bit of spare time, so I thought it'd be nice to attend a conference. Yeah, I'm going to talk about how I used Xarray during my PhD and how it facilitated my work and some of the things I got on with it. So in this talk, I'm going to give a brief introduction to fusion energy, which I thought might be interesting, change the pace a little bit from what we've heard so far. I will try to keep it brief, but there's a lot to cover, as I'm sure you can imagine. Then I'll talk about my PhD and the kind of how that fits in, and then how exactly I used Xarray and how I kind of wrangled my data to get it into a form where Xarray was useful. And then talk about some of the things I do and don't and would like to see in Xarray. So first things first, fusion happens in the sun. It's a great nuclear reaction that we can potentially utilize for commercial energy production. And basically, it is combining two nuclei together into a form where they are more energetically favorable, and then utilizing that extra energy that you gain from doing so and extracting it somehow. So generally, how we're going to do that on Earth, as opposed to in a star, is with the DT reaction, the deuterium-tritium reaction. So we've got here a deuterium, which is just a hydrogen with an extra proton, and a tritium, which is a hydrogen with two extra protons. Combine those together and you get a helium, and then you got one spare neutron, which carries out all of your extra energy, basically. So if we want to do this on Earth, we've got to get a deuterium-tritium gas and heat it up a lot, so that the average energy of each collision in that gas is high enough to overcome the repulsion between the like charges in the tritium and the deuterium. So to do that, we heat up a gas. It heats up a lot. We got to get it to like 200 million degrees or something like that. And that's very hot. That is so hot that we can't contain it with any known materials. So we have to use magnetic fields. So it's what we call magnetic confinement fusion, or MCF, and generally that's done using a tokamak. I know I'm using a lot of words here. I'll try and get through this quickly. So tokamak is basically just a loop of electromagnets, basically making the magnetic field go in a torus shape, a donut shape, as you can see here. For reasons that aren't really important to non-fusion physicists, we have to add an extra magnetic field component to make the field lines go around in a spiral. That's what makes a tokamak, but basically all you need to know is that you've got this big torus, big donut-shaped plasma, and it's very, very hot. And so one of the major problems with getting fusion to commercial scale is that you have to have an exhaust region, basically. Some part of your plasma, due to the way magnetic fields work, will be in contact with your vessel. And so you've got to have an exhaust region to deal with this. And if we scale up to commercial sized reactors, that exhaust region gets too hot. We can't have any materials in the way of the plasma. It's a big problem. So we in the UK at CCFE, we've built a device called MAST-U, Mast Upgrade, which is trying out an experimental exhaust region, which is going to try and mitigate this problem by basically moving the exhaust region further away from the main plasma. So on the left here, we've got a cross section of our MAST-U tokamak where you've got the main plasma here, which is very hot. All the particles leave the plasma here and then stream down these field lines. I don't know if you can see my mouse, actually. That might not be very useful.
We can see
It's
it.
visible.
Cool. So yeah, so moving it further away, you basically allow the particles to become slower over time. And so they reach the exhaust region with less energy. You can also do it in a separate chamber, which is what we're doing here. And you can pump in some neutral gas to cool everything down as well. But in essence, we are testing this exhaust configuration, and we need to know what the temperature and density of the plasma is in that region. So that's where kind of I come in. I use Langmuir probes, which are a form of plasma diagnostic, which you can use to measure temperature and density. To do so, you need to insert a bit of metal into the plasma, not really insert in a fusion plasma because it's way too hot. But you insert it in, you apply a voltage, and you change that voltage over time. That voltage allows you to select the energy of stuff that is hitting the probe and being collected as current. And so you've got a voltage and a current, which gives you an IV characteristic. If anyone's familiar with electronics, that's quite a common way of evaluating a component. We're just doing that with a plasma, basically. So here is an example of an IV characteristic, which has got the voltage sweep on the bottom and the probe current on the y-axis. And by interpreting this IV characteristic, you can gain information of the temperature and the density, basically. In tokamaks, this is a bit of a problem using Langmuir probes because, as I said, it's way too harsh of an environment to have you just stick something into the plasma. And the fact that you've got these very strong magnetic fields also complicates the analysis. So basically you end up with this strong angular dependence. And so my PhD was basically investigating whether this design of probe we have on MAST-U, which has an interesting designed tip to try and mitigate this angular dependence, I was trying to verify whether that worked. And I was kind of doing that in two main ways. That one was through simulations, and one was through experiment. I did manage to use Xarray in helping me answer both those questions, but I'll be talking a bit more about the experiment today than the simulation stuff. So this is a video from one of the experiments I did. So I took some probes from our tokamak in the UK to a linear device, which is basically the same thing as a tokamak, but just in a straight line. Obviously, the field lines aren't contained in a straight line. There's one end. Basically, you start your plasma at one end and it flows down the field lines to the other end. But that was what I wanted. I wanted to control the angle of the probes were exposed to, basically, and see how that changed our measurements. So this is a little video of that happening. So the bright white bit here is the plasma, and there is my probes moving into position there, and they're constantly scanning voltage and measuring the current as they do so, and then they move back out of position. And that whole cycle is what we call a shot. I did shots at various different angles with various different plasmas, with various different magnetic field strengths and so forth. So I ended up with quite a big dimensional data set, basically. And so what I wanted to end up with is this on the left, which is a series of IV characteristics, which I can interpret. And so my job was what I ended up doing was using Xarray to get from my raw data taken here to these IV characteristics here. And so this is a kind of example of the raw data I got out of my my measurements, and it's really interesting trying to approach it from getting stuff into Xarray, because you have to kind of analyze the dimensionality of your data set in an interesting way. So I had this shot time, so this is just like real time that was going past. But what I was actually interested in was the time for each sweep of voltage, basically. And there is a slight difference also between the up sweep and the down sweep. And so I wanted to average those together. And also for a single shot, I had different values of B field, plasma species, incidence angle, and measurements taken with a different diagnostic, which provided another measurement of temperature. That's called Thompson scattering. You don't need to worry about that, basically. So what I ended up with was a data set that looks a bit like this, which hopefully some of you will now recognize a bit more what's going on. So I had my dimensions being probes. There are 4 different types of probes that I was measuring with. Tilt being the incidence angle. Time here is referring to the sweep time. And the TS radial position is the different coordinates of the separate diagnostic that was measuring, basically. And I was able to combine all this together. Xarray very, very nicely allowed me to average the sweeps together, both the up and the down, and all of the different sweeps together into one individual sweep. And so I've got this these voltage, current, and decurrent, which is the error in the current data variables. Yeah, and I was left with this lovely data set that I was able to interpret. Basically, for this, basically what I ended up doing was for each scan of some parameter, I would make a separate data set, but I probably could have combined those together if I wanted to. And so this is how I produced the plot, basically. So you've got your data set. What I'm trying to show here is how nice it is to just kind of, when you've put all that hard work in to get your data set together, how easy it is then to kind of use it to have a look at what's in your data set. And so it's very easy just to kind of go from left to right here to understand the logic that's being applied. So you can see that you just select the probe you want. So this probe's called L. You select the position of certain angles. So in this case, I wanted basically every other angle up to 10. So I made a slice for that. And then for each of those tilt values, I went through and selected it and then plotted it. Unfortunately, it doesn't seem like Xarray supports error bars just yet. I did see an issue on that somewhere back in the archives, but I'm not entirely sure why it wasn't then implemented. I'm sure there is an interesting reason for that. But yeah, but this is how I got to my end result, and yeah, it was great. I was then able to kind of like look at my data much more interestingly, or get the interesting things out of my data, I should say. And yeah, and in a similar way, at some point, I asked myself, do I want to have a look at the parameter space that I was having a look at? And that wasn't a problem to get that information out of Xarray, basically. You've got my metadata data set, which is just the other diagnostics measurements, basically. And I was able to select the maximum temperature, which I previously calculated. I realized you could probably do this in a nicer way where you reduce over the TS radial position coordinate, but I'd already done that. So here I've got the maximum temperature. I want to plot that as a line graph against the maximum density and just, yeah, some extra plotting stuff. And I ended up with this graph. Obviously not exactly this graph because the colors aren't quite right. I've slightly cheated here, but you get the essence of how I was using it. So yeah, the thing that I was doing most with Xarray that I didn't quite figure out how to do was applying kind of custom functions across dimensions. And I'm sure that there is a very easy way to do this, or there is an avenue to be able to do this, but I couldn't quite figure it out, especially not in my particular way. So what I ended up doing was making a function which takes in a particular subset of the data set and then iterates over some dimension and then spits out another data set, which I then merge back into my main one. As I say, there's probably an easier way to do this, but I couldn't quite figure it out for what I wanted to do. In fact, the main thing I wanted to do was curve fitting. And I think curve fitting is now a part of the main Xarray branch. So yeah, just a little bit too late, unfortunately. So in summary, some of the things that I like about Xarray is it's very neat and it's very easy to understand the commands, just going from left to right, as opposed to using something like NumPy. I didn't list them here, but there was a lot of fast operations on my larger data sets that were just so easy to implement, so quick once I got there. And it's easy to combine as well disparate data sets together. I ended up being able to actually combine my experimental and my simulation data sets together into one place. Not that it was particularly useful for my PhD, it was just a nice thing to be able to do. The thing I don't like about it, and I'm not sure there is really a solution to this because it's kind of implementation specific, is that there was a lot of work that went into getting my data into the right format so I could get it into a data set. So yeah, but as I say, it's difficult for that to be kind of solved out of the box. So things I would like, maybe it would be more transparent docs for creating data sets, because I know a lot of, as was said, that a lot of the users for Xarray are geoscientists. And a lot of that is done using netcdf files and stuff like that, but there's not many examples for other ways of getting data into your data sets. As I also previously said, I'd like some curve fitting, but it seems like that's been done now. So I should probably go have a play with that at some point. Also, having an easy way to apply a function over a dimension, as I say, probably already exists, but I couldn't figure out how to do it. And my chief gripe would be an error bar potting function, but there we go. Yeah, that's my talk. Thank you very much for listening.
Thank you, Jack. That was an interesting talk. For the audience, if you have questions, please put them in the chat or unmute yourself and ask.
Cool.
Aya, do you mind unmuting yourself and asking?
Oh, I might have to stop sharing. Can I see the? I can't see the chat.
So
there we go. Yeah.
So we have one question from Aya, who asks, what was your choice of your experiments data input format before creating the Xarray collections?
So basically using NumPy files, or like pickle files, basically, which was not a particularly nice way of doing it. Getting it into Xarray so I could convert it to a netcdf was actually kind of one of the objectives of learning how to use Xarray and kind of wrangling in that way. I mean, all the raw data is in binary files and stuff, but I don't think that's what your question's asking.
Have you, this is just a comment from me, have you looked into Xarray?
Is that, I've heard of it, but I've not looked into it much.
It might be a good thing to look into.
Okay, what exactly is it, if you don't mind me asking?
So it's, okay, I'll try. So you're familiar with netcdf, at least you know netcdf, and Xarray is trying to basically do the same thing as netcdf, but in a different way. And what I mean by that is, so Xarray has built-in like chunking, like where it's basically saving each chunk to its own file, which kind of makes it easy to work with Dask, since you can load its chunks separately. Mm-hmm. It has built-in compression and a bunch of other things that basically it's a pluggable file format, right, as compared to netcdf.
Probably especially if you have really big data, Xarray is a good idea. So like things measured in gigabytes or terabytes, or maybe even more.
Yeah, not fitting into memory type deal, right? Yeah.
Any other questions?
Can I ask one more question on the data wrangling thing?
Mm-hmm.
I was curious, maybe you could say a little more, but was that like just like I guess about like finding ways to sort of combine together your, or maybe you could say a little more about what was hard about data wrangling, why it was harder than you thought it should be.
I think what I found difficult about it was first visualizing how I should change my data into the format which is kind of more Xarray friendly, and I found a way to do that, and that was fine. But I think constructing a database from that data was not exactly clear how I should do that from the documentation. I think what I ended up doing was creating lots of smaller databases and kind of combining them together, like stacking them along certain dimensions, which I think is the way you're supposed to do it, but there might be easier ways that I've not come across, basically.
Yeah, I mean, I'll also mention there's this project, this external project called XYZPy that I think might actually be kind of what you're looking for, but we should think about ways to sort of build this into Xarray proper, because this is, I agree, it's a little painful. Yeah.
Mm-hmm. Okay.
Other questions?
I feel like we could do with some documentation that's not aimed at someone whose data is already like on a regular grid of squares, where you've just got some like mess of different files, which is pretty common in science, and then you have got to organize them somehow, and it just has like various suggestions for how to do that.
Yeah, definitely. Yeah, one of the things I had a problem with was the other diagnostic I was using did not have regularly taken measurements. So basically, I had to average all of those and was losing information in doing so to combine them into my main data set. So yeah, I definitely agree that there should be some documentation on that.
Okay, looks like we don't have any other question. Oh.
It might also be a case where when we eventually get the data tree suggestion implemented, then this will become easier, because if you've got two different diagnostics which have some shared dimensions, but they're not exactly the same, that's a really good candidate for using like a data tree structure that's working at a higher level than a single data set.
Good point, Tom. All right. I'd like to thank our speaker again. Thank you, Jack.
Thank you.
And let's now move to our next speaker, who is Ravin Kumar, who's going to talk about Bayesian modeling with ArviZ and Xarray. Ravin, all right.
All right, am I muted? You guys can hear me?
We can hear you, and we see your screen.
All right, great. So I'm going to talk about ArviZ and Xarray, and I'll tweet out these slides later. The whole notebook is self-contained. So I'll start with what is ArviZ, because I think people know what Xarray is now. ArviZ is a Python package meant for the Bayesian statisticians, particularly to help them in their workflow. So ArviZ in particular doesn't do the Bayesian estimation portion, which we'll talk about a little bit later, but it does help Bayesian users with all the other tasks, such as analysis of the results, data storage, plotting, diagnostics, and all that. Over here are some of the plots that tell us different things about Bayesian models, and this is one of the outputs of ArviZ. So Xarray is a pretty critical and crucial dependency of the library, and we'll talk more about that in a second. So who am I? Talked about this a little bit. I'm definitely an Xarray user, an ArviZ user myself. I'm a core developer on a PyMC3, which is a probabilistic programming language. This is the thing that actually gets all the samples and the stuff we'll see later. And the core developer on ArviZ itself. I use Xarray and all these tools in business settings. And here's my Twitter credentials and whatnot. So how do ArviZ developers and users feel about Xarray? I don't know if the text is large enough on this slide, but hopefully you guys can read this. It's pretty great. The users really like it a lot, and we like it as developers. So why though? There's just multiple reasons. Xarray contains everything in such a nice way that it makes the single user workflow really, really nice with labels and easy indexing and all of that. Same as in all the other spaces that we just saw, but it's the exact same thing in the Bayesian setting. But there's two other things that really, really are nice on top of that. One is Xarray allows for data serialization to disks, so group collaboration is super easy. It's not just Python objects in memory, but now we can put these things onto I don't know, SSDs or S3 or whatever, and someone else around the globe or in your team can reuse the results. And the biggest thing for us on the developer standpoint is because there's such nice data consistency in labels, it makes for an easy API, and it makes something easy to develop on. So rather than having to pass in 6 or 7 arrays to a Python function signature, you just pass in an Xarray object, and ArviZ can just magically figure out where everything is. So what we've done in the ArviZ project in particular is we've taken Xarray and we've wrapped it around this thing called inference data. So in statistics, inference is like what you're trying to do. You're trying to infer something about the world. So this is the inference data object contains all the data that we need to make inference. And what it essentially is it's an object that has Xarray data sets as each one of its, we call them groups, but each one of its attributes. And it includes some additional functionality to aid with the Bayesian workflow. And one of them actually is serializing to netcdf4. So this whole thing gets packaged up and can be written to disk and a netcdf4 file format. But I mean, it is bad form for me as a statistician to make a bunch of claims without giving you any data. It's just poor form. Somebody would call me out. So I ran an exhaustive survey. And here it is for reproducibility. We're all about reproducibility. So I sat an ArviZ user down in a chair and asked him 10 times whether he liked Xarray and ArviZ. This isn't as cool as a nuclear fusion experiment, but hopefully it suffices for these purposes. And we got a bunch of data. So here it is. I asked that user, no bias, obviously, whether they like Xarray, and we got 9 trues and 1 false out of 10 samples. And luckily, we have this handy file format to, this handy object to put everything into. The big thing, though, with statistics is we need to infer what is the sort of unobservable user preference. So we have 10 samples, which is great, but just like the classical 10 dice rolls or 10 coin flips, it could just be a fluke that you ended up with 9 out of 10. Like, how do we not know if we ran the experiment 100 times, it would be a sort of different proportion? So what we want to do is we want to figure out what the latent user preference is and what the what the probability of each, the proportion of yeses or nos would have been, or trues or false in this case. So in Bayesian statistics, what Bayesian statisticians usually look for is what's called a posterior distribution that gives you, it sort of describes the probability of each event occurring. And if it's a little abstract, we'll get to a concrete example in a second. So what I've done here is I've taken our Xarray object, and it's over here in the data as the data argument for this observed, and I put it into this PyMC3 model. So this is a fully formed Bayesian model. I have this latent parameter, which is uniform. It's the true proportion of what we'd expect if we ran an infinite amount of questions. There's some boilerplate for PyMC3 to run, and then here is the actual MCMC sampling. So one nuance about Bayesian statistics is there's a lot of ways to get to the posterior, but one of the most popular ways these days is this thing called Markov chain Monte Carlo, where it's essentially a guess and check. You make really good proposals, you see whether they're good or not, and then if they're good, you accept them, and all that. And that also might be abstract. So here is a video from Colin Carroll that shows sort of what's happening. You take a bunch of samples, and over time, you end up getting sort of this hourglass effect with sand, and you start seeing peaks and valleys where things are likely to be true and valleys where they're unlikely to be true. But what happens is you get a ton of floating point numbers, like a lot, like tens of thousands of them. And luckily, we can take all these floating point numbers and put them into an Xarray data set. And what that makes it nice, by having this nice file format, what makes it nice for users and for developers is we can just take this one Xarray data set, pass it to ArviZ. So here is a plot trace function, and we start getting diagnostics. So I don't have to worry about there being 4 chains or 4,000 samples or this dimension or this sort of label. It's so nicely packaged that we can just take one object, give it to ArviZ, and it just does this thing. So this is a diagnostic that MCMC Bayesian users use all the time. It tells you whether your chains converge or not. A nuance about MCMC is it's not a guaranteed algorithm to be like correct every time. So you have to double check that things worked out. And in this case, they did. But what we're really looking for is that posterior plot that tells you the proportion of what our estimated latent proportion is of true or false. So what this plot is telling us is that it's unlikely that no one likes Xarray, that less than 10% of users, or we get 10% false on the question. But it is likely that we'd get between 64 and let's say 100 if we ran this sample 100 times. Or if we ran it a million times, you get 640,000 or 990,000. And as expected, it's probably around like 80% of trues and false for the question, do you like Xarray as an ArviZ user? And this is what tells us the latent space of what is of our unobservable parameter of the, I'm tripping over words here, the latent representation of Xarray preferences for ArviZ users. Wow, it's a lot of words. But it gets worse for Bayesian users, unfortunately. Posteriors are just one thing. So posterior samples are just one data set that we use. We also we want the log likelihood that comes off of the sampler. And so we want to capture that somewhere. So we've got this other ArviZ data set, Xarray data set. We've got sample statistics, which is another data set that's given off by the sampler. And we've got our observed data. And it's not just like we need one Xarray data set. We need a bunch of them to be able to do our work. And this is where the inference data comes in. It sort of captures or holds all these various Xarray data sets. And to point that out, all we did in that one thing was this one step, fitting a model to data. in a full Bayesian workflow, there's actually a lot of steps. And this even actually is a simplified representation. There's this really great paper that Gelman and his group just published that shows you the full workflow, and it's even scarier than this. So there turns out to be a ton of different arrays, and they're all multidimensional, and you can get lost in them pretty easily. So here is us loading in a pre-computed Xarray ArviZ data set. I didn't want you all to wait 5 minutes for sampler to run. And it's got a subset of the number of Xarray data sets reviewed. So a new ones on here that you haven't seen before: prior predictive checks, and so on. The good news, though, is computing these arrays takes a long time. It's really nice to be able to write them to disk. So we can take an inference data and we can say to netcdf, and inference data supports the groups. I'll say like the groups function of netcdf, and Xarray data sets just happen to fit exactly in a netcdf. So we can take everything, we can write it to disk, and then that means that we can load it up later without having to run the entire workflow again. Sometimes that workflow takes literally hours to compute on a modern PC. So I've got like an 8-core Intel desktop, and some of the runs take like 30-40 minutes. I don't want to run the inference step over and over again. I just want to be able to sort of load and look at my plots later without having to wait 2 hours each time to do that. And so remembering this picture, this is how we got there. We needed an easy way to be able to cut across, let's say, chains or draws or samples or variables or whatever. And a single Xarray data set helps. It's fantastic for that. Whoops. But we have a bunch of Xarray data sets, and ArviZ inference data captures all of them. And as a bonus, besides making things easy to keep track of in memory, lets us serialize things to disk so we can load it to and from memory as we need. So what was life before inference data? It was pretty painful, to be honest. I think this is the core problem that Xarray solves. It's not fun to debug arrays that have like a whole bunch of indices, and you have to like remember what 0 and 100 and where these things were. And I think everyone likes this about Xarray, but for Bayesian specifically, it also solves a problem in that there were incompatible formats between different probabilistic programming languages. So Stan is a very popular probabilistic programming language that implements MCMC, and there's a lot of uses there. There's NumPyro, there's Turing and Julia, there's PyMC3. If somebody did their work in one PPL, the samples would be valid, but it would mean sometimes that they would be really tied to that particular probabilistic programming language. ArviZ and Xarray abstract that away, and if you end up with an inference data object, no matter which PPL you generated it from, you can use it with ArviZ to criticize and share and share results. Every probabilistic programming language had their own diagnostics because they had their own data format. So everyone had to rewrite the same functions over and over again, which was sort of a waste in the open source community and annoying for users to switch between libraries. So Xarray and its nice packaging makes it easy to make ArviZ, which makes it easy to make the functionality generic. And then serializing everything disk, running things takes forever. So you have 2 minutes. Serializing everything to disk makes it much easier to share results. So again, Xarray enables a better single user workflow. It enables a better multi-user workflow, and it enables a really nice API for the developers of ArviZ to give to Bayesian users. And it also makes our lives easier on the internals of the ArviZ packaging. But where did that one false come from? I have to admit, it's not all I don't know, sunshine and roses. Just like the previous example, and Jack talking about that, occasionally it feels like it's tricky to get exactly what you need out of Xarray. The API is doing a lot of complicated things nicely, but sometimes you've got these edge cases, and so here's one of them for us. But the nice thing about Xarray is the developers provided a lot of escape hatches to like NumPy or pandas data frames, so you can sort of just finagle your way to one of those, and you're sort of good to go. But to go 2 comments back, what are we 100% sure about? We really like working with the Xarray devs. They're absolutely fantastic. When we reach out and ask questions, they're super, super responsive to us. A number of the Xarray devs who are here had a meeting with the ArviZ devs and gave us their time and insight and feedback on whether things we were doing were right or not. So I think as Stefan was saying earlier, if you've got an idea, you really the Xarray devs are just happy to talk to you. So, just reach out to them, share your idea. They'll give you feedback, and you can go do your open source thing and feel comfortable that you've got this fantastic library and team that's giving you functionality to do what you need to do. So this is the Dask conference. What about that? Sorry, the Dask summit. Well, Dask is fantastic too. We're integrating Dask into ArviZ for the problems that we just talked about earlier, which is dealing with out of memory sort of diagnostics and sampling. So it's really great that Xarray and Dask work together as well. And so it's really just this. Xarray and ArviZ work super closely together at the code level and I'd say even at the developer level. It's really nice that the tools make it really easy for the end user not to have to worry about really Xarray or ArviZ, but their inference problem and the science that they're trying to do instead of fighting a bunch of arrays and all of that. Shameless plug for me. Me and 2 other PyMC devs are going to publish a book where we talk about computational Bayesian methods, and we use Xarray a lot. Actually, I don't think we could have written a book without Xarray because it's the file format we use to pretty much plot everything. If you're interested more in how computational methods are used with Bayesian stuff, there's an interest form, and I send out details like every month about when the book is going to be published. This is this will be the cover image. So more information on everything I just said is at all these links, and I am happy to open it up for questions.
Thank you, Ravin. Yeah, we actually have a couple questions. Okay, so first question, can you share advice on creating a dataset of datasets, especially if datasets wrapped by your inference data superclass might hold quite different dimensions?
Yeah, so ArviZ implements a bunch of methods that take the standard formats from like PyMC3, TensorFlow, probability, NumPy, and a bunch of others, and it automatically creates the Xarray dataset for you. So you just take the output of your Bayesian model. Let me just jump to the code to make it easy. Where's my model? It's right here. So you can there's a function that's like AZ from like PyMC3, and you just give it your trace. If this was the trace, and I know I might be using words that not everyone knows here, but ArviZ implements a bunch of methods which magically take the common PPL formats and turn it into Xarray. If not, ArviZ has some additional functionality that that takes dictionaries or even an Xarray data set of its own and turns it into an inference data. So there's a lot of IO methods in ArviZ, but what they're really doing is they're really just taking whatever you provide and like turning it into Xarray data sets under the hood. Yeah, so I'd say read the docs on that one. I can send the documentation as well.
Good. So we have one more question. Is it possible for ArviZ to manage datasets that also have real-world coordinates, time, space, to go along with the variables posterior, prior, and observations?
Yes. So I mean, I'd say ArviZ can do it because Xarray can do it, right? Xarray implements that functionality, and because we use the dataset object in its full glory, it does the same thing. In terms of specifically though, does ArviZ have good time series functionality? The ArviZ time series functionality is a little limited right now. So you can run your Bayesian model. You can do your and I'm actually working on a problem at my work right now that is a time series problem. And so Xarray and ArviZ by extension can hold the time series just quite well. But if you're talking about ArviZ functionality to handle time series, like plotting, things like that, we have a Google Summer of Code project specifically focused on this. So there should be a lot of new developments in the next 10 weeks.
Good. And then there's a quite popular request to have links in the chat. Could you actually post those in the Slack channel at some point?
Yeah,
please?
I will. I'll put them in the Slack, and I'll put them in this chat, and then I have to join the Dask Slack. But if not, you can. I'll tweet this out.
Yeah, you can just put this here, and then I'll put them in the Slack channel.
Okay, great.
Okay. Oh, thanks.
I'll tweet out these slides as well, and so hopefully you can find them. Cool.
Sounds good. All right. So that was the last question. So thank you, Ravin. That was a really good talk. And so our final talk is from Davis Bennett, who's going to talk about Xarray and Dask in the life sciences. Davis? Okay.
Am I visible and audible?
Yeah, we can see your screen and
okay.
can hear you. All right.
Yeah, so I'm going to talk about Xarray and Dask and the life sciences. I work at Janelia Research Campus, which is a neuroscience and molecular tools development institute funded by HHMI. And I work specifically with a project team that's called the Cell Organelle Segmentation in Electron Microscopy Project Team. The acronym is COSEM. And my job is basically to ensure that a lot of large imaging data sets are organized on local and cloud storage. And I triage a lot of the manipulations to the data sets and logistics for the data sets. And in the process of doing so, I use Dask and Xarray a lot. And I did my PhD also at Janelia, and there I used Dask for large 4-dimensional light sheet microscopy data sets. And I really should have used Xarray, but I didn't. And I regret that. But I know better now. So what is COSEM trying to do? On the left, we have an image of a high resolution EM of just a single slice through a cell. And you see lots of structure there. And on the right, we have the same cell, but with semantic labels applied on top of the structure that we recognize. So we're specifically trying to identify structures like the plasma membrane, the endoplasmic reticulum, the mitochondria, vesicles, the nucleus, all of these substructures within the cell that are of great interest to biologists and are hard to infer just from the grayscale imagery. This is electron microscopy, so you don't get color. You just get one channel out of your data. And so we're using machine learning to basically take this single channel data and infer basically a set of multi-channel prediction layers from it. So how does this work? We take a large EM data set and then generate ground truth data for training the models by isolating little cubes of the data. And so this is what a slice through one of those tiny cubes would look like. This is what the whole data set would look like with cross sections rendered. And these are all the little ground truth cubes. And then within that cube, a human being, not me, fortunately, a human being goes through and essentially applies an integer label to every voxel inside the cube. And the integer labels correspond to structures of interest. And so this is what the grayscale would look like, and this is what the labeled image would look like. And then here's a mesh rendering of one of these densely labeled ground truth cubes. And these are all the classes that we're ultimately trying to predict. And this ground truth data is used to train deep convolutional neural networks that are going to consume grayscale data and emit essentially a prediction for all of these classes. And it was actually these cubes, I came into the project team not using Xarray as a core part of my kit. And then it's working with these cubes that pushed me over the edge and made me like hard commit to using Xarray. Because these cubes differ from the raw data in terms of their offset. So they have a physical offset in space. And they also have a different grid spacing. These cubes are basically super sampled to a higher resolution. And I made a variety of simple programming errors, like getting the offset wrong, getting the scaling wrong, and it was driving me crazy. And so I thought, what if I could just, have a data structure that includes the offset and the scaling in it, and I don't need to worry about it. And that was exactly what the problem that Xarray solved. So about our data sets, the acquisition method is basically a cell or a tissue is frozen or fixed, and then a poison is added that like leaves a heavy metal in the membranes of the cell, and then a focused ion beam, which is basically like a laser made of metal ions, you can think of it that way, blasts a layer of material off the cell, and then we take a picture with an electron microscope. And this is repeated, and you end up with a sequence of 2D planes that together have a nearly isotropic resolution, and you can combine them to form a 3D volume. So we typically have a voxel grid spacing of 4 to 8 nanometers, and for reference, the thickness of the plasma membrane around your cells and around the ER and around the nucleus is on the order of 5 to 8 nanometers. So we're approaching the resolution that lets us see inside the plasma membrane. We can resolve protein complexes like ribosomes, which is pretty cool. We can't see anything inside them, but we can see that they're there. And so our typical data set dimensions are on the order of 10,000 by 2,000 by 10,000 voxels. And that's in X, Y, and Z. And the data types we work with, the raw data is acquired at, it's actually acquired as a 16-bit integer because it's converted from a voltage to an int. And then we often receive it in the form of a 8-bit integer. The actual bit depth isn't much more than 8 bits. And then we generate a lot of derived data that is unsigned integer types from 8 to 64. And we're trying to scale back on our production of uint64s because they're very big. So there's some sociological considerations. I receive data sets from a lot of different groups. A lot of people have ended up with these EM data sets, and they often give them to us and they want us to generate some kind of predictions with our machine learning models. And often they come to me in a variety of formats, maybe without the right metadata. Also, I have to deal with, I have the pleasure of working with a lot of Java tooling in the bioimaging space. And the axis order in that ecosystem is flipped relative to the C, Python, NumPy axis order. And this means that if I were doing everything with NumPy or Dask arrays, and I didn't have any semantics for my array indices, I would be getting into axis order bugs all the time. Because often you'll encounter metadata that doesn't specify which axis has 4 nanometer resolution. It just gives you a list of resolutions. And you have to know based on the metadata, is this XYZ or ZYX? And so to deal with these irregularities, I need software tools that are flexible, explicit, and sort of capable of abstracting over the differences between the types of file formats I'm given and the nature of the metadata that might be associated with them. So I've been using internally Xarray data arrays as just like a common data model for all of the EM data that I work with. And it's been like incredible at preventing these axis indexing order problems, being explicit about scaling and translation through coordinates, and also metadata related errors. And so this is just an example of this is like the equivalent of my personal toolbox or my my contractor's truck with all the stuff on the back. But this is a library that I use called FibSem tools, and I have a read Xarray function that's polymorphic over all the different, or a lot of the different file formats we encounter and a lot of our bespoke metadata formats. But the input is a string, in this case, a S3 URL. And this is accessing an N5 volume, which you can think of as just Xarr with a hierarchical chunk storage. And I'm accessing something that I've stored on S3. And we've got some metadata in here. And the resolution is right. And I can just work with this data and do all my processing on it because I've accepted Xarray and Dask as like lingua franca of my code. So Xarray has been extremely useful there. I haven't gotten a lot of other people using this yet within my group. So there's an evangelism component that I need to work on more. So for data storage, we store our data in N5, which is essentially isomorphic to Xarr, and Xarr Python supports the N5 format. And it's really important for us to visualize data sets. And that's because often somebody will give us a data set that they've pre-processed in some way or another, or they think the data set is isotropic resolution, but because it's so big and they're using crappy tools, they just haven't looked at it. Like they did something to it and they think, oh, it's probably they've maybe inherited some description of what's in the metadata or what's in the data set, and they never actually looked at it because it's such a chore. So they apply a new mutation on top of the data and they give it to us. And so the first thing I always want to do is just look at the data and sanity check and see, is there anything there? Does it look the way it's supposed to look? And so we use a tool from Google, not an official Google product, but made by a very enterprising Google engineer called NeuroGlancer, to view, and it natively supports large chunked arrays. But you can't just have one array with NeuroGlancer. Even if it's a nicely chunked Xarr N5 array, what you really want is the ability to zoom in and out at different scale levels. And so to interactively browse a 10K cubed image essentially requires a storage optimization in the form of multi-resolution pyramids. And so I'll give you a little demo of that. We have this website that is a catalog of our cloud accessible data sets. And so I will just view one of the data sets we have on S3 with NeuroGlancer. And so you see chunks are loading in. They're coming in the form of these cubes. And now this is a macrophage cell. You can see all the nice sort of ruffles coming off the membrane. And I'm going to zoom in, and you're going to see these cubes. I'll just zoom in like this. You're going to see cubes kind of increasing the resolution as we zoom in. And these really are cubes. It's chunked in 3D. And so this is the heterochromatin or the euchromatin. I always forget. This is the nucleus over here. These are mitochondria. This is just a whole ton of organelles. This looks like it's the Golgi. But as we zoom in more, you'll see the resolution basically increases as we zoom in. And so the way we do this is we have it, instead of saving our data as a single array, we save it as a collection of Xarray and 5 arrays, where each one has been downsampled relative to the full resolution data. And then depending on what the field of view I'm trying to look at the data at, NeuralGlancer is smart about requesting only those chunks that make sense given the field of view that I have. So when I'm zoomed out, we use the low resolution, and when I'm zoomed all the way in, then we can afford to bring in the high resolution chunks. This is a very standard rendering technique. Now will this resume where I left off? Yeah, okay. So there weren't good tools for making multi-resolution images in a coordinate-aware fashion with lazy data structures in the Python ecosystem. So I wrote a library just called Xarray Multiscale that facilitates this process. So it's generic over dimensions. It internally uses Xarray data arrays for tracking coordinates, because something that bit me and the previous implementations of multi-resolution pyramids, including the implementation in scikit-image, they don't account for the offset that occurs when you downsample an image. So if I downsample an image by a factor of 2, I'm actually changing where the beginning of the first pixel is every single time I downsample. And if you just have a collection of NumPy arrays, that information is completely lost. So you might think, if you try and plot, for example, the output of the scikit-image pyramid Gaussian function, there's no indication that they don't share the same origin. But I was delighted to find that with the Xarray data arrays, I can explicitly encode and track that the act of downsampling has moved my image over. And also for visualizing a multi-resolution pyramid, the fact that despite the change in offset, they all still have essentially the same coordinate bounds means that plotting them, visualizing them is much more intuitive. So this is the result of, this is just showing the Xarray multiscale. It's basically one key function that does it. You give it data, which is going to be coerced to Xarray data array, and then a reducing function, and then the scales that you want to downsample by. And under the hood right now, this is using Dask array coarsen. It's not using the Xarray coarsen yet, because I want to plug in potentially arbitrary reducing functions. And it wasn't clear to me how that would be done with Xarray coarsen, but maybe that's something to talk about. And then the result is a collection of data arrays, where each data array, and I don't do this recursively, I'm thinking about adding that, but each data array is basically the result of taking the input data and then applying this function with different parameters. So if you visualize this as a dependency graph, all of these depend on the highest resolution data. Alternatively, I could have done it where each one depends on the previous one if you have a reduction method that supports, that's basically linear. But I want to support modal downsampling, and that's not linear. So I need a scheme like this. But I found that the data array data structure was extremely natural for this, because it just tracks all the coordinates and I don't have to worry about it. So an area where things stop being quite so natural is that I haven't yet found a good data structure for representing the collection of multi-resolution images. And the Xarray dataset model doesn't quite work for it. So in this example, I create a multi-scale collection of images, and then I put them in a dictionary, I give them names, and then I make a data set from them. And then I do the ISL query to get the first index of all the elements, or the element at the first index in all the arrays in the collection. And so for the first highest resolution data, we get 0. And then for everything else, we get nan. Because basically the Xarray data set, it wants all of the subarrays to basically be on the same grid. And so that means that at index 0 of the first data value, or the first resolution level, there's actually nothing there, because for all the other lower resolution levels, because they're all shifted over by an offset. So it pads with nans. So this isn't quite what you want. And so I think the solution to this, and there's some GitHub issues about it, is to extend the Xarray data set to encompass data structures where you have a whole bunch of views of the same coordinate space, but the views are gridded at an increasing level of coarseness. I don't think it's an incredibly hard or terribly interesting computer science problem. It's just a matter of coming up with the right interface. So some more sociology. I think within life sciences, there's a tremendous potential for Dask and Xarray. We're still thawing from our MATLAB winter. There's still a lot of people who are using tools that don't scale, and their data is getting big enough that they need to scale. So I've had, within Genele, I've had a lot of experiences where people have started using Python for processing their data, but they don't know about Dask and they don't know about Xarray. And so telling people about these things, these tools, has often led to people actually using them, which is extremely rewarding. And my dream is to have just an end-to-end Dask Xarray pipeline where we have raw data that is the way it is because it came out of the microscope that way. But everything else, all the way to the machine learning predictions that's run on a GPU, for all of that, we describe it as a sequence of lazy operations where the intermediate currency between those operations is an Xarray data array. And then if you want to apply, if you want to manipulate that transformation and sample the output, you can do it all in memory without generating a bunch of stuff on disk, a bunch of intermediate results. But we're pretty far away from that. So yeah, that's my presentation. Any questions?
Thank you, Davis. So yeah, we have 4 minutes, so we'll probably take one question. And it looks like actually we have a question from Tom. Have you seen the discussions about a potential Xarray data tree higher level structure?
I have not. Is that a discussion I should look at?
Definitely, that's pretty much what you're suggesting, I think.
Okay.
Definitely give that a read.
Is that linked somewhere? Maybe in...
I stuck the GitHub link in the chat.
Okay, wonderful.
All right. Could probably take one more question, but it doesn't look like there's any. Go ahead.
A sort of a related question. I guess there are kind of maybe 2 ways you might think about, I guess, representing these sort of tree-like structures. One version would be to say that you have like a multi-scale array, like a single array that exists on a bunch of scales. Another version might be to say that you have a multi-scale data set, or for example, you have say different parts of a data set that exists on different scales. I don't. Do you have any thoughts about which of those makes sort of more sense?
So my mental model of the multi-resolution image is that it's one coordinate space, and that when I index into that one coordinate space, the arity of the result should be a function of the number of resolution levels I have. And so I would basically, I think I would like to say, I want to have the data at 1010 in real units. And then what comes back is like 5 things if I have 5 resolution levels. Now, nobody does the API like that. The way it always works in the consuming software is the software like NeuralGlancer says, oh, okay, we're really zoomed out. So what we need is scale level 5. And so then it goes into indexes scale level 5. Alternatively, NeuralGlancer, if everything's lazy, NeuralGlancer or some other visualization tool can just say, oh, we need data from position 10. It gets back something that's a list of lazy things. And then it says, oh, okay, based on where we are, let's only take the lowest resolution and actually compute that. That to me is more natural. So that's how I think about it, but I could be wrong.
All right. Unfortunately, we're coming to the end. So I just wanted to take time to thank our speakers. I think the talks were really engaging and informative. And hopefully we continue these discussions asynchronously on issue trackers and things like that. And also I wanted to thank our audience for the questions, and also to thank the organizers of the Dask Summit. So yeah, this was good. We should probably do it again. I hope you have a good rest of the day. With that, we'll just wrap things up. Thank you, everyone.